3 is about the structure of ionic solids. So when we are categorizing solids, we can group them into crystalline solids and amorphous solids. Crystalline solids have a highly regular arrangement of their components, and amorphous solids are considerably disordered in their structures. A great way to think about it is chocolate. So when you, like I like to watch baking shows every once in a while, and they talk about tempering chocolate. So when you have chocolate and it doesn't cool slowly to a certain temperature, then it might, when it rehardens, it might get that like the discoloration, or it might get like light brown, or it doesn't look very nice. There's not that shine to it that bakers want to have on their desserts. So the amorphous version of chocolate would be that dull, not shiny, there's that filmy covering over the chocolate. A crystalline solid would be like the perfect chocolate, where it has a sheen to it, it looks beautiful. That would be the crystalline. Okay, so crystalline solids are usually formed by slowly making them. They're a lot slower to make than amorphous. The positions of the components in a crystalline solid are usually represented by what's called a lattice, which is a 3D system of points designating the positions of the components, which could be atoms, ions, or molecules that make up the substance. The smallest repeating unit of the lattice is called the unit cell. So this is in your notes. This is on page 461 in your textbook, in case you want to look at it more. But the top row are the unit cells that we have, and we did body-centered cubic and face-centered cubic. We learned about those in Chem 1. I don't think we did simple cubic. But the lattice is just combining lots of those simple unit cells together. Okay, so it's just repeating in patterns for how the atoms are arranged in that crystalline structure. And then the space-filling unit cell just shows how the atoms actually touch each other, versus the top two, they're not actually touching. So it just kind of shows how the atoms are arranged like that. And that's how we see a lot of times with ionic solids. That's how they are represented in those lattices. So the energy required to dissociate an ionic solid into gaseous ions, which is called lattice energy, for two compounds is shown in the table. On the basis of Coulomb's law, which of the following best helps to explain the large difference between the lattice energies of sodium fluoride and magnesium fluoride? So sodium fluoride has a lattice energy of 930 kilojoules per mole, and magnesium fluoride has 2,978 kilojoules per mole. So which of these choices best helps to explain the large difference between the two? Okay, we have solubility, we have electronegativity, we have masses, and we have charges. Okay, well, we haven't really talked about solubility much yet this year, but solubility usually has to do with dissolving in water, and we're not talking about dissolving these in water. We're talking about lattice energy is turning from a solid to a gas. Okay, so I would say that A would not be a good choice because of that. There's probably more reasons than that, but that's where we are today. The electronegativity of magnesium is greater than that of sodium. That is true. If you look on the periodic table, magnesium is next to sodium, and it is one step closer to fluorine, so that means that, yes, it has a higher electronegativity. But electronegativity means that it wants electrons. And do cations want electrons? No, they don't. They want to get rid of them. So that doesn't help us explain the lattice energy, because in the compound form, sodium and magnesium have already lost their electrons. They don't want to gain them back. So they would rather stay put than change. So that's not going to be a good choice either. Cross off B. Help us narrow things down. The mass of the magnesium cation is greater than that of the mass of the sodium cation, or the charge. Now the correct answer, because we're getting down to it, the correct answer is D, the charge. This goes back to what we talked about in 2.2, where we said that when you have higher charged ions, that makes for stronger attractions. Okay, so the sodium has a +1 charge versus the magnesium has a +2 charge. So since the magnesium has a +2 charge, that makes it bond stronger to the fluorine than the sodium. And that's because it has an extra electron to give to fluorine to create more bonds in that system. Okay, so the correct answer is D. That is the end of 2.3.